know, in your final project till the end of this class, you will do a LNA design. The LNA design, what you will do is to choose a transistor, and then you design circuits like which bias the transistor and do the impedance matching. Also, you will need to do an antenna design, but that's another training. So today, we're gonna start from a basic transistor, and then we will teach you how to use the software ADS to design it, how to use it. I know some of you may not have basic knowledges about some parameters. For example, noise figure, stability. Please, I send you the lecture files. Please read them. I think that's enough for you to catch up everything. And if you have questions, please read the document first, and then if you still cannot understand, you can come to us, both TAs. We're working on this session, and I think it's very important for you to learn the basics and learn how to use ADS before you start your final project. Your final project for students, the whole process should be roughly more than 3 weeks. So try to start as early as possible. In your final exam week, you will have other class maybe, so it's very hard for you to get time. And later you will do fabrication test as well. And if this is not one time successful, you have to repeat. So prepare a lot of time. I recommend you start if you never do it, start before 1 month before, it's better. So okay. And
yeah.
Okay. Today we will start the ADS. So today's training, it's better you all of you work on our computer, so the classroom computer, because we know the version here is all the same. If you have some problem, maybe we solve for the whole class. We don't need to debug on your own PC, so this is better for us. And it's also, you can install this software on your workstation or on your PC after this class, and that's better for you to do your design homework. Okay, today Yimin will teach you to verify the transistor till the layout design, and we will record the whole session. We estimate the session may take roughly 2 hours. So if you have a class after 2:30, you can leave. But if you don't, it's better you stay here, and you can follow us step by step on the PC or in this classroom. And so later on, you can try your own when you're back home. So any questions before we start the training?
Okay.
So then this to Yimin.
Yeah, so let's get started. And so I think before we start the amplifier design, let's go through some really just basic concepts. And you can find the reference of this kind of discussion in the Pozar Microwave Engineering book, chapter 12. So there is a complete chapter showing you the process of amplifier design. So the way we look at the amplifier in the microwave circuit is that it's a two-port network, and you can see here. And the unique feature of this kind of amplifier is that it has a very high value S21, but low value S12, so that it makes sure that most power is getting amplified from port 1 into port 2, and there is a high isolation from port 2 to port 1. But as you can see, because we are using the real transistors, so it is not ideal, and therefore the S21, which means the port 1 affected by port 2, is never zero in the ideal case. It means that the transmission coefficient, which means the power to the load from the source, is actually determined from both the source impedance as well as the load impedance. And and therefore, in this case, there are two kind of gain describing the circuit. So the first gain is the transducer gain, and the second gain is the available gain. And if I want to describe this briefly, the transducer gain is actually, in the real circuit, the power delivered from the source to the load. And the maximum available gain is that given a source impedance, you are trying to tune the load impedance so that it gets the maximum power. And so we are actually designing we're actually designed to get the maximum available power gain. In that case, we will need to design a source impedance, and then we will look for the optimum load impedance. And I will show you the complete step using the template in the ADS in this session. And another important factor of the LNA design is the noise figure. So when we talk about the noise figure, we need to first get some concept of the noise signal to noise ratio. So the noise figure of this network describes the deterioration of this device. So there is a noise there is a signal noise ratio in the source port, and there is another signal noise ratio at the output port. And by inserting this amplifier, we're actually getting a worse and worse noise signal to noise ratio as we cascade the circuit as follows. So the overall gain of this low noise amplifier is that we want to have a as low noise figure as possible. But in the later session, you will see that there is a lack of a trade-off between the noise figure and as well as the maximum available power gain. But you can see the overall process, the key components is the source impedance. This is actually an arbitrary value we are choosing, and we are hoping that this kind of impedance will maximize the gain and lower the noise figure. And another important chart designing these amplifiers is the contour plots over the Smith chart describing the noise figure, describing the gain, and we can show this process later. So let's get to the ADS. So first, we will see the main page. This is like the main. This is like the project manager folder of the ADS, and then the first step is we are going to either create a workspace or unarchive the SPICE model from the blackboard. So in this process, we are going to just directly archive the device model. And because we are using the 55143 for this tutorial, by the way, do you have access to the device model in your computers, or is like a...
Yes, do you?
Then we archive this. We need to assign a folder, but make sure that there is no empty spaces in the folder path because of like software compatibility issues. Yeah, for this example, I would I'll just change another name into my folder. Okay. And you just need to follow the default sections, like using the ADS compatible technology and also the technology file, assign this technology file, and also the name of this library. Just need to follow the defaults. And finally click finish, and then it will unarchive and open the workspace. So right now you see there is like only one folder or one cell. So the concept of the cell in ADS is basically just the concept of a component, like in other EDA softwares. And in each component, you can assign a schematic describing the circuit, a symbol which shows the reference of the ports, to be imported to other schematics, and also other file, which is the layout of the cell, which means just the footprint of this component. So I think the first step we need to do is we need to assign the value of the assign the unit of the layout. So in this way, we need to click the option technology setup. So the technology in ADS, it just means the design is similar to a design rules in the PCB layout, which show describing the minimum unit of the layout and also some resolution of your layout. So once we click the technology setup, and in the layout units, we change from mil to millimeters. So it will be helpful when you change the layout, change the unit when we do the packaging of your device. And for the resolution, I think we can just follow the default value, which is a very high resolution for the PCB process. And then we click apply and OK. And now we have assigned the unit. So once we, do you have any? Yes, what kind of issue are going?
Technology cannot be saved for units. Database resolution or type of technology
You need to close the schematic. So you need to, when you change technology, you need to close every file open in the project. And then you apply and okay, you can change that. But I'm going to give you a warning of changing the technology file. So when you change the file, change the technology, basically the ADS will just rewrite the units in the layout file, so it will not rescale the layout. Which means that previously, if you give like a layout in the mil units and you change the millimeters, the file, the dimensions of the layout will not change. So the actual size of the layout actually shrinks according to the units. Okay, so once we have this device model, we can first double-click the schematics. So in this step, we are just want to update the SPICE model because this is a very old ADS file. So we need to make sure that the model description is compatible with the new ADS. So once we open this, you can see that the model has two parts. The first part is just the FET, the fetch SPICE model, and other are just the passive RLCs and transmission lines, showing the package of the interconnect. So first you select the FET1 file and double click to open it. And you don't need to change anything, change everything, and just write OK. So it means that for the ADS, it will read the device model and update to the latest version. And the second step is you select the advanced circuit 2 model, which it has the MOSFET 1. So you double click to open this, and you don't need to change anything, and then you click OK. Once you update this device models, you click save and you close it. Okay, so we're going to design with this transistor. So the first design is we're doing a DC simulation. The way we're doing this is first we click this new schematic window, click this button, and we assign like a new schematic and a new cell to the DC sweeping. So for my case, I will say sim0/DC, and you create this new schematic to do the DC sweeping. And also during this DC sweeping, it's a good chance for you to check whether the SPICE model matches the datasheet provided. So you now have like an empty workspace. So on the left part, there is a part tab where you can add your simulation setups and also components into the schematics. But here we need to just insert a template. So here there's an insert. In the insert menu, template, you can find there are some provided templates. And in this case, we are just selecting the DC FET. You can see there are also other templates, but we are just do the DC sweeping of the FET. We just select this template and OK. And now you can see there are some parts following your mouse, and you just need to click somewhere to assign this component's location. Now you have in your schematics, you have the FET curve tracer and also a simulation variable defining the display variables, and also some simulation setups showing the sweep of your VGS and VDS. So the next step is we just import our components from our previous library. So in the parts tab, there is like a library browser. You open this library browser, and you can see there are 3 libraries provided. So we are just selecting the workspace libraries, and you can see there are 2 components. So this component matches the name of the cell. So if we click this first component, and then we double click it, and then you can see there is like a component following a mouse in the schematics. So that in this case, and once you click one, you just need to press escape so that you can quit the component creating mode. And then you have imported the model into the schematics. So the next step is just you need to give the connection of the gate and the drain and the source. So in the DC sweeping, the quick way to the key shortcut to create wires is Control+W. And also there is a button here to insert wire. So in this section, you just need to connect the gate to the gate. So I want to make it like in the prettier direction. Gate to the gate, and then drain to the drain. As for source, press escape, and then there is also another button, insert ground, and you can insert ground to these 2 pins as a ground. And then you can save this file, and now you can see the device is connected to the FFET curve tracer, and then we are assigning the sweeping values of the VGS and VDS. If you look at the datasheet of the device, maybe you can see from this figure. So that there is like a typical IV curve of this device. So I'm just going to give it a highlight. Yes, so okay, here you can see in the datasheet the VDS sweeps from 0 to 6 volts, but it displays from 7. So we can sweep from 0 to 7 volts for the VDS, and for the VGS from 0.3 volts to 0.7 volts. So we are following the same sweeping as we have in the datasheet. So VGS start is 0.3 volts, stop is 0.7 volts, and there are 5 points. VDS start from 0 to 7 volts, and you can assign it to 71 volts. Now 71 points, yeah. Start from 0 to 7 volts with 71 points. Okay, then we just need to simulate. We click the gear icon to simulate, and once we click it, it will run the DC sweeping. And with it to finish, it will automatically pops up a result window. And in the result window, we can see this the first figure, which is the drain current over bias of VDS and VGS. So we can double click this curve or this plot, and we want to change the Y scale matching the datasheet. So on the Y-axis, we disable the auto scale, and we plot this curve from 0 to 70 milliamps, which is 0.07, and with a step of 10 milliamps, with 0.01, and we press OK. And now we have like a curve similar to our datasheet. So in the simulation, we can see that as we sweep the VGS from 0.4 to 0.5 volts, and near around the 2.5 volts, we can see the current it sweeps from around the 7 milliamps to 23 milliamps. And if you look at the datasheet of the same sweeping value of 0.4 to 0.5 volts at around 2.5 volts by VDS biasing, we would have like a very similar a level of biasing. But as we increase the gate voltage to above 0.5 volts, so the datasheet shows that the current never exceeds 20 milliamps. But in our SPICE model, we can see that when the VGS is over 0.5 volts, we can see the current is basically larger than the datasheet. So it means that in our simulation, we want to have a VGS around the 0.4 volts so that we can match the SPICE model with the datasheet. And this is also a very important point for your design and your choice of transistors. So we can also move the M1 marker to the biasing point we want to choose. So it's like we are giving like a 2.7 volts, but with around 10 milliamps of current. It means that we need to give like the VGS a little bit higher current. Okay, so once we know the suitable value of biasing voltage of VGS and VDS, we are going to do the next step, which is the S parameter simulation of the device given our biasing. So in the project manager, I think the first step is we just close all the open window and leaving only the project manager, and then we create another simulation, which is Sim2, I think, Sim1, S parameter. I would say S param. And then we created another schematics. We want to create another schematic to simulate the S parameters given our biasing conditions. So we create an empty schematic. We click the design guide, amplifier, and then in the amplifier design guide in the second tab, S parameter simulation, we can click the first one, which is S parameters, noise figure, stability curve and group delay. So this one describes all the design specs we need for the amplifier design, and we click OK. So it will import a complete template. So we first we can close this report first, and in the schematics we can see in this simulation it has like a SMP file. We just need to delete it, and we need to use our own model. So we select this file and we delete, and we just tidy this simulation a little bit, and then we import our transistor from the component library. Double click it to import it. So with the component, of course, first thing is we need to assign our DC biasing. So the way we are doing this is we need to have a DC voltage connecting to the gate and drain, and then adding the DC block, and then we connect the S parameter terms into this model. So with our component, first we can just search in the search all library. We just write a DC, and then there is an option of VDC, which is the biasing voltage, DC voltage source. Okay, so we click the VDC for one voltage for the gate and another voltage for the drain. And we first add the ground to the DC voltage, and then we assign the gate voltage value. So the gate voltage is 0.425 volts because we want to have a slightly higher voltage than 0.4 volts, and the drain voltage in our simulation we are giving it 2.7 volts, which is like a typical value from the datasheet. And I think for your amplifier circuits, you will notice that the fabricated circuit will not always follow the same biasing. So in that case, you need to give your like a VDC voltage to your amplifier, and you need to tune the gate voltage so that it will have the same current as your design and also the datasheet. So with these two voltage, and the next step is we are going to connect this. So in the search session, then we need to also the same DC, but here there are also other two parts. So first we click the DC feed part. So we also search DC when we click the DC feed. So this is just an ideal inductor, or there are other ways, but so you can use ideal inductors, which is DC feed, and also ideal capacitors, which is DC block. But also you can just also type L. So there's also an inductor. So once you click inductor, you can find the two inductors here. So yeah, in this case, we are showing the layout using the inductors and capacitors. So for the inductor, we are typing 100 nanohenry. And this is actually a very large value at 2 gigahertz. So yeah, we are designing LNA. In this demo, we are designing this at 2 gigahertz. So the inductance was showing a very large impedance at this frequency. There's gate and drain voltage. Okay, so once we connect these two, the next step is we are assigning the DC block, which is capacitor. Okay, so the next step is we are inserting the capacitor, which is C. We first search C, and then we click the search the capacitor component. When we do the layout, if we press Control, press R, we can actually rotate this capacitor. So we need 2 capacitors, and we press Escape. We double click the C equals this one. We can directly type in 100 picofarad for this C, and also for this one as well. 100 picofarad. And the next step is we are going to connect the DC block to the gate, drain into our simulation ports. once we have this layout, also we first cancel our search so that we can choose the library of components. We first assign it to simulation DC, and then we insert a DC simulation so that with this simulation we can annotate and plot the node voltage and current in our following simulations. Then we can also click the gear button and run the simulations. Before that, we also need to assign our sweeping voltage. So here we are starting from 1.0 voltage to 3.0 gigahertz, not voltage, 1 gigahertz to 3 gigahertz with 0.1 gigahertz of sweep, and so we need to calculate the noise. And for other options such as the system impedance as well as the temperature, we are just following the default value. We are just sweeping the frequency from 1 to 3 gigahertz, which is basically the most of the frequency range in which you are assigned like design specs. Okay, so once assigned the frequency sweep and with the device model, we click the gear button and then run the simulation. So I think the first step is because we added a DC simulation, we annotate the voltage and current. So here in the simulation DC annotation, we can annotate the voltage and the pin current. We first annotate the voltage, and also in the simulation DC annotation, annotate pin current. So we can see that when we have 2.7 volts of biasing and also of drain biasing with a 0.425 volts, we are having 9.8 milliamps of current. So it's getting close to the value provided by datasheet. So with this kind of biasing setup, which it means we're having this assigned gate and the drain voltage, then we can run the S parameter simulation. I think right now in this simulation, the DC simulation is actually having a higher priority of this S parameter and also with the simulation templates. So we just need to delete this. We delete this DC simulation, and then we run this again. So it will calculate the S parameters as well as the gains and noise figures. Okay, so in the updated plot, as you can see, there are a lot of circles in the S parameters in the Smith chart. So basically, in this kind of simulation, what it does is that it sweeps the source impedance, and for each source impedance point in the Smith chart, it calculates the corresponding gain, transducer gain, available power gain, and noise figure, and then it plots the contour of the source impedance with the same gain, same noise figure in the two different colors. So here you can see in the brown color, it is the noise figure gain, noise figure plot. It means that if you follow the source impedance in the same curve as the contour, it will have a same level of noise figure. And also in the blue curve, it is actually the available gain, which means that if you move your source impedance following the blue curve, blue contour, the amplifier will give you like the same level of power gain. So you can see that these two curves, these two kind of colors of circles does not always overlap, and the centers of this, which means the maximum gain and the minimum noise figure, these 2 points does not overlap. So it means that you need to have like a trade-off between the gain and noise figure depending on the source impedance you are selecting. So also in the template, because we are designing at 2 gigahertz, so we will move our marker in the frequency selector. We move it to 2 gigahertz. And you can see these curves also change as we move with the frequency. Okay, so I think this is actually the most important step of your amplifier design, which is assigning a source impedance and expecting a trading off between the gain and the noise figure. And before we proceed, I can show you one iteration of this design with our slides. So in this design, we have first follow the first iteration in our presentation. in this report, we are selecting the minimum noise figure, and you can see that in the plot, and there is actually a row here with the which is the noise figure minimum, and here in this tab, the software automatically gives you the source impedance with the minimum noise figure and the maximum gain at this case. But also another thing is for the amplifier is the stability factor, which is K. And if you want to find more description of this one, you can follow the Pozart book, Pozart chapter 12. There is like a stability section. So the reason why the amplifier is not stable is because of the S12, because it is not an ideal amplifier. So there is some kind of feedback from port 2 to port 1. So under some worst cases, if you have like a strong reflection from the load and you have a high level of S12, then it means the power it will go back and forth between the 1 and 2 ports of the amplifier. So there is like some stability criterion, and the one we are using in the simulation is the stability factor K. And for an amplifier with a K larger than 1, it means that the amplifier will always stay stable at whatever source impedance and the load impedance you're choosing. So, but in this case, we are having like a 0.685. It means that if you look at the red curve, and it means that if you move your source impedance somewhere inside this red contour, the amplifier will become unstable. So it is not a good starting point of our design, because at some part is not stable. So we are only designing a 2 gigahertz frequency, but we are not sure if the curve, if our like a source impedance will move into the unstable curve. So we want to make the K larger than 1. So the technique we are using is that to stabilize this amplifier is we are adding another shunt resistance for 40 ohms to the drain of our design. So you can find this kind of technique in our provided slides, provided lecture slides of the microwave engineering amplifier design. So by adding this 40 ohms, you can see the stability factor now. In this slide, it rises from 0.6 to 1.9. It means that at this kind of frequency, the amplifier will be always stable given whatever source and load impedance. And also under this case, we can see the software shows that if we give this kind of level of source impedance, we would have a minimum noise figure as well as 13.89 dB of gain, given this kind of optimum load impedance. So in this example, we are selecting the point to the minimum noise figure. So we are now having like a goal of our impedance matching design, which is the optimum source and load impedance. So the next step, following the slides, is we are now using our stops, using a transmission line and also an open stop to match the 50 ohm source impedance, to convert that impedance into our required source and load impedance. And notice that when we talk about the impedance, input impedance or port impedance, we need to have like a concept of the reference plane. So in our previous section, what the source and load impedance provided are the impedance we're looking from the amplifier into the port. So if you see here, this is the transistor and this is the network. So this source impedance is actually what we want when we look from the transistor into the port. But it also means that if we look at the same kind of impedance with a conjugate matching, under that case, we'll have a maximum power delivery of conjugate matching. And if we look at the impedance from the network into the transistor, we would have a minus J value instead of a positive J. So because we're designing a conjugate matching. And the reason why we emphasize this kind of the direction we look of the port and impedance we are looking into is that when we're using the design guide of the inside the ADS, it will force like the direction of impedance matching from port 2 into port 1. So that the direction of matching at the gate and at the drain are different. So you need to be careful of the polarity of the impedance polarity when you are doing the conjugate matching. And we are showing this in our later session, but in this case, if we follow this session, and then we will obtain the two transmission lines with the frequency and the electrical length, and also we will do this line calculator to convert the electrical delay into the real size of the microstrip line. So once we finish the input and output impedance matching, we would get like a microstrip line circuit, which is this circuit. So with this circuit, when we do the complete simulation, we would have like a 1.9 stability factor and 0.56 minimum noise figure. But you can see there's a trade-off here. We are in this design, we are achieving a minimum noise figure. But if you look at S11 at 2 gigahertz, we only have minus 4.1 dB. It means that we are having a very bad matching. So I think for your design specs, maybe you need to make sure that your S11 should be below 10 dB for good matching. So it means that you cannot, simply moving your marker to your minimum noise figure point. So you need to trade off between your gain and noise figure. So it means that in our following steps, we are not choosing this optimum point. We are choosing another point instead. So here you can see that we are choosing so in this circle, there are two center points. So if there's a blue dot and there is a brown dot, the blue dot is the point with the maximum gain, and the brown dot is with the minimum noise figure. So now we are having a trade-off. Is that we put a marker into somewhere of the center line between these two dots. So it means that if you want to have a higher gain, you can move your marker along that line closer to the blue dot. And if you want to have a lower noise figure, you also need to move your marker closer to the noise figure, so to the brown dot. And also you can change the plot of your noise figure contours, because I think in your design, in your design specifications, you need to have a minimum level of noise figure. So you need to plot that contour and make sure your source impedance is inside that circle. Okay, so we will follow the same kind of impedance here. So let me just go back to our ADS. First step is we need to add a 40 ohm resistance to make the circuit stable. So we minimize this tab, and in the simulation, we just type R to search the libraries. We type R, and with the first component is the resistor, and we click this so that we can plot the resistor here. I think you just need to place the resistor somewhere before the DC block, so it will not seen by the RF, but it also maybe I'll put it here, yeah. And I change the impedance to 40 ohm and make it grounded. Okay. So we're adding a 40 ohm resistance connecting the drain to the ground. Once you finish this 40 ohm resistance to stabilize the amplifier, you can simulate it again. Now you can see in the updated plot, we were having a K factor 1.9, which is larger than 1, and you cannot see the red curve in the Smith chart. And also in the gain and the noise figure plot, you will see two contours with 2 points, and we are trading off between these two. By moving our gamma S marker along this line, and you put somewhere in between these two lines, maybe here. So let's try moving our markers to match this with our design goals. I think this location is actually the point where we are choosing to trade off. So we are having 0.787 noise figure with 15.848 dB of gain. And you see this marker is locating in the line between the 2 points. Okay, so once you know this, the designer will automatically give you the source impedance and load impedance you need to have this noise figure and gain. So I will just highlight this for our further impedance tuning. Okay, so I think the next step we are doing is we are creating the microstrip lines to convert the 50 ohm impedance into our required impedance. Okay, I think after we create this microstrip line, we can take a short break. And then in our design session here, I think what we need to do is we we create a Smith chart component here. In the library, we first find the Smith chart. The Smith chart matching is the library we are using. Once we click the Smith chart matching, there is only one component, which is the Smith chart. If you find the Smith chart matching Smith chart button, then you click this and you can assign, you can place this smart component. So in this hint, it shows that when you are using the smart component, you also need to follow the design guide. You can just click OK, and then you can assign. Maybe you just need to place it here, place somewhere. Yeah. And there is one important thing of this Smith chart is that in this utility, it will always try to convert the impedance from the port 2 to the port 1. And you can see there is like a short line here. There's a short line. It shows that this part with the short line is the port 1. So in this utility, it will always look into the impedance from port 2 to port 1. It means that in our example, we are having a source and load impedance. We are always looking from our amplifier towards the source. So with this Smith chart, you can see we are connecting port 2 to the 50 ohm and port 1 to our source. So when the Smith chart finish the design, it will always convert the impedance from port 2 to port 1. And therefore, we are giving like our desired resistance, yeah, in this case. So the next step is you click the design guide. You click the design guide and amplifier, also amplifier. So there is a tools here. Tools, you click the Smith chart utility. So in this utility, it will automatically design the matching circuit based on our Smith chart component. So and you click OK. So here there is like a sync. You want to select between update component from utility. So I think you just follow the basic step. Just update the component from this utility. So with this open utility, the first step is you need to make sure you select the correct schematic. So you select this schematic and we are clicking the first component. So the first component will do the impedance matching for the source impedance. And in the utility, we can see that the port 1 is the impedance we want to get, and port 2 is the reference impedance. So here, when we click in the network schematic of the utility, when we click port 2, we are making sure it's 50 ohm. Value is 50 ohm. So in the port 1, we need to assign our source value, source impedance, which is 29.471 plus J 54.266. And then we also need to change the frequency of our Smith chart from 1 to, because we are designing at 2 gigahertz. So also in the frequency tab, we are assigning 2 gigahertz. Okay, so now what we have is we are designing the matching network at 2 gigahertz, and it will convert the port 2 50 ohm into the port 1 of the source impedance, which is this value, and then we lock both source and the load impedance. Okay, so next step is we are designing the impedance converting circuit using a through line and also an open line. So first we click the schematic to deselect the ports, and then we can see that it's first 50 ohm and then it's going to our impedance. So first we need to click the open stop to move the point from the center of 50 ohm into somewhere below the 50 ohm. And once you click this open line, you can see as I move the cursor, the port impedance is now moving from the 50 ohm away. And you need to move some location with the same radius as the port 1 impedance. Maybe so here we are having like a similar radius. So first we can settle it here. And the next step is we are using a transmission line. So we now have like an open stop, and then we are clicking the transmission line. And in this case, you can see it will follow the circuit. it looks like we are having a shorter line, but that's okay. We first click and create this line, and then we select the open line. Once we select the open line, we select in the network schematic. Once we select it, we can drag this point to make sure that, the curve overlaps, and then we can click the through line to further fine-tune our desired impedance into the impedance we want. Okay, so once you finish this, you click the build ADS circuit. You click this build ADS circuit, and when it finishes, you can select this component, and you press, there is an arrow button here, is push down into hierarchy, which means you can see the sub-circuit. And you can see it's already created with the transmission line and also with the open stop from port 1 to port 2. Okay, so we are so let's look into the hierarchy and make sure we are getting the same value of these two stops. So the next step is we are doing the same thing for the load impedance. We first push out the hierarchy, and then we click. We run the same design guide. I think I didn't close it, so I can find the Smith. We go back to Smith chart utility, and we are selecting. In this case, we're selecting the component to second one, which is the load impedance. So in the second one, again, we are assigning the frequency at 2 gigahertz. Also, we are assigning 50 ohm to the port 2, and we are assigning port 1 to our desired load impedance, which is 22.922 plus J 11.405. And you once created these two, you also need to log these two impedance. We just repeat the process to match the load impedance as well. So we first step is we use an open stop to move the 50 ohm away from the center point and into somewhere with the same circle curve with the same radius towards the impedance we're looking. So again, open stop and then transmission line. And you can fine-tune these two by selecting first the component you want to tune in the schematic, network schematic, and then you drag the point you want to move so that our desired load impedance it stays within. When it says the node is locked, it means we are selecting the wrong impedance, but that's fine because it means that we are getting a very close value. Okay, and once we design this network, we also build ADS circuit again. So there is a build ADS circuit button, and we click this, it will build a circuit. So when you finish, we can push into the hierarchy of Smith chart 2 and see if we get the circuit. So the next step is we were going to convert this ideal transmission line into the real microstrip lines. So the most important tool we're using is the line calc in ADS. So when we select the tools, line calc, we can start the line calc here. And in our example, we are designing a microstrip line. So type microstrip line, ID microstrip line default, and we can assign our substrate permittivities. And in the substrate permittivity, we are assigning 4.0 in this case, just as an example. Also, the height, the h, is the substrate thickness. Here we are assigning 2.5 millimeters, so it is a very thick FR4 board. As for T, which is actually a copper thickness, we can assign it to 50 micron, which is 50 micron. And we are following the same kind of conductivity and loss tangent. Just as an example, I think you need to type in the value you have measured in the lab 2. Now we have the permittivity, substrate thickness, copper thickness, and conductivity. Then we assign the component, the frequency we are designing. We are designing at 2 gigahertz with the Z node. We can type in 50 ohm, and the phase delay. So this delay, it should be the same value as we want to replace in our schematics. So for the ease of convenience, I would push into the source transmission lines. Yeah, so this is the source, and this is the load. So with the line calc, you just need to replace the electrical length with the length of the ideal lines. So first we can replace at 78.5 in my case, and then we can synthesize. Before synthesize, we want to change the unit to millimeters as well, and then we can try synthesize. And now we are getting the width as well as the length of the microstrip line. Yeah, synthesize. We click synthesize, we can calculate, but also we can analyze from the width and length we want. Here we are doing the synthesize. So let me just, as a very quick way of illustration, I will just copy, I will just record this value here. And the length of another stop is 56.03. And we synthesize this again. And we are having another kind of a length. So what we do next is we manually replace this microstrip line into the real models. So here I'm just doing the same process for the source and the load transmission lines. For the next step is 49.56 degree, and we synthesize this again. And another part is 40.78. We synthesize this again. Okay, I think we can save this kind of line calc so that we don't need to type in the parameter all the time. So we click File Save, and in this case, we just we can type in FR4. Yeah, we can just save it, so that next time we don't want to type in the same information again. Or, yeah. And another thing is that the line calc is like a very independent software in ADS, so it does not have very good synchronization between the software with the schematics. So we need to record this value as well. And then we are creating the components of these stops. So first, maybe you can first calculate this width and length of your lines, and you need to record this line. You record these values. So right now I'm just copying, making some snapshots of this value. So I think the next step is we are importing the transmission line circuit model here. So in the library, we click TL lines microstrip. So you can see there are a lot of components. So the first component is we click this M sub, which is the definition of the microstrip substrate. So in the M sub, we need to type in the same information with the H, height 2.5 millimeters, the substrate thickness, and permittivity 4.0 substrate, and T, which is the copper thickness 50 micron. No loss tangent in this simulation. Okay, so we have created the microstrip definition.
And also the substrate thickness is also medium. Okay. So next step is we are creating the transmission line components. So as we drag down the buttons, you can see there is a M line, which is the microstrip line. It's just a through line, and also MLOC, which is the open circuit stub. So we just need to have this one stub here and another open stub, circuit stub. But I think for this model, you can also leave one part of this microstrip line open as an open circuit. So I will just use this value. So we are first creating the microstrip lines for the source impedance. So we need an open stub and also another kind of through line. Because of the Smith chart utility, the left side is like a port 1, and in our case, our port 1 is connected up somewhere above. So we are assigning this TL1 as the TL1 in the Smith chart and TL2 as the TL2. And the next step is we need to assign the shape of this line. So the width here, the width we have is 5.08. 5.08 or 185. I just click type in the complete value, and the length here is 18.5175. Yeah. So this is the first transmission line, and the next one is the open stub. The open stub has the same length, 5.08185. And the length is 13.217. So this is the open stub, and this is the transmission line. So next is we just need, once we have this transmission line, we just need to disable the Smith chart. By disable, we can, there is like a button with a red cross. Yeah. Oh, I forgot 0.5. Yeah. So next step is we replace this model with this. So we just need to disable the Smith chart by clicking the red cross. So now this component is disabled and is open circuit. And then we can connect the wires of the transmission line. To the port, and another open line to the open line, and then we connect this input to the port 1. And now we have the input circuit. So the next step is we follow the same for the load as well. So I just need to copy this line with the same length and change it, same width and change its length. So from the drain or from the load point, also we need to create 2 lines. Yeah. So the first length is 11.6908. The second length is 9.61965.
稍微慢一点，他们还没做完前面那边的，就把图放一下，我看看。稍等等。
Also, we're doing the same step for the load as well. We just need to disable the ideal transmission line and replace it with the real transmission lines. Okay.
这做完然后仿真一次就休息，然后正好
Okay.
查一下。
TL3 is flipped, right? Because port 1 is connected to, or is it supposed to be like this?
What do you mean?
So if I look at the other one,
Port 2?
no, TL1.
Port 1?
To L3, the ports are flipped, or is it supposed to be like this?
Where is it flipped?
So TL1 and TL3, right? Where the dash is on port 1.
Yeah. So for this transmission lines, the port 1 and port 2 doesn't matter.
Okay, I see.
Because it's reciprocal and also symmetrical. So in this case, it doesn't matter. Okay, so once we have the line, we can run another simulation. In the simulation, we can create a new plot, just plot the S parameters. So once we click the gear button, and it runs the simulation, and besides this plot, we can create a new plot by clicking this kind of grid rectangular plot, and we can click it somewhere new, and we just need to select the S11 in dB, S12 in dB, 21 in dB, and 22. Just double click, and then we can select the dB. And once we click, we can have our plot. So this is actually the behavior of the transistor, of our amplifier with our impedance matching network. And by clicking, there is like a red triangular button in the menus. We can insert a marker on our plots. We can probe the S11 and also the S21, which is now is the transducer power gain. Now we can see it has a minus 12 dB of matching, and also with 18.8 dB of gain. And if we want to plot our noise figure and also stability factors, we can also create a new plot. And by choosing the noise figure NF2, which is the noise figure of port 2, we can plot our double click the NF2, which is the noise figure we want, and we can have our noise figure here. Also, by choosing our marker, we can try to get like 0.7 of a noise figure. New plot NF2, which is a noise figure. And if we want to plot the stability factor, we want to define that variable in our simulation. So in the simulation file, we sweep to simulation as parameters, simulation as param library, and as we drop down our figure, we can see there is like a stability factor button. We click this button and we put this definition into our schematics. And you see this component, it has like an equation which is stability factor 1 equals some kind of calculation, and we can directly refer this variable in our plot after the simulation. Okay, so I think once we have this stability factor, we run the simulation again, and in the plot we can create a new plot and showing the stability factor, which is the step fact 1. We can add this in the plot, and we are having a stability factor with our microstrip line circuit, which is 1.9. So I think that's it. So you can see the overall process is like 3 steps. The first step is you choose the source impedance, and the simulation will give you the noise figure and the optimum load impedance. And the next step is you do the impedance matching from the 50 ohm into the required source and the load impedance with the ideal microstrip line. And the third step is you convert the ideal microstrip line into the microstrip line with the real dimensions and with the real substrates. And I think once you get these 3 figures, then you're doing well with the LNA design.
Okay, guys. I think all of you are good at this stage. So in the coming hour, we will transfer this schematic simulation to a layout. Like, hope we can finish in 1 hour. And then you can like archive everything, archive your workspace, send to your workstation. Later on, you will run again, like go through today's simulation by yourself. So I'll give this to Yiming, and he will teach you how to do the layout.
Okay. So I think the first step, of course, is we save a copy, or we save as. So the next we can maybe as same for layout. We create this like a completely new schematic, so we don't want to affect our original design. So in the same for layout, now we have the schematic, and we don't need we don't also need the symbol, so we just need to leave the schematics. And let's just try what happened if we generate a layout based on what we have in this kind of simulation file. So we can click layout and generate layout. So we can follow with the default options, and we can click OK. And you can see there is quite a mess in the layout. Yeah, in this layout, you can see there is like a transmission lines, which is what we want, and also there are also other components with this really weird symbol. With this, it basically means that we need to create some kind of footprints for our components instead of using this kind of like symbols for the layout. So we can close this layout, and we can delete it. We don't need to save this layout. We can close this layout, and we delete this layout. So the next step is we need to create the footprint for our transistors and also for our inductors and capacitors. So the way we do this is that first we go to the transistor cell, and once we open the schematic of the transistor, again we can save as. It means that we are going to modify our library. We are just need to create a layout without the simulation data. So here we can change this name to layout, to the transistors layout. We can save this design as a layout. And before we step into the symbol and the schematics, the first thing we need to do is we open the layout and we copy the layout from the datasheet. It basically describes the pad. So right now I have the layout, recommended layout in the datasheet, and we just need to pin this snapshot as a quick reference. Yeah. So you can see in the layout there are, from the left side we have layers, and on the right side we have properties. So on the left side layers, you can see there are a lot of layers, and the most important layers we are using is conduct and conduct 2. So the conduct layer is basically the top layer of the board we are using, and conduct 2 is the ground plane we are using. And right now we are creating only the footprints. So
how do you open the layer stack?
I think it's in the views, docking windows, layers window. Yeah, with this window open, you can have a view of the layer. So we click the conductor layer, and we select this layer. And the next, by creating the insert rectangle, you can create a rectangle. So because we are just following the layout of the pad, so once we select this pad and we look at the property, there is width and height. So the width of this layout is 60 millimeters, and the height of this pad is 1 millimeter, or maybe okay. So the width is 0.6 millimeter. Yeah, and the height is 1 millimeter. Also, we move it back, lower F and Y to 0, so we move it back to the origin. So this is the first pad. The key properties are the width and height, and also the location. So next we're creating another pad. We first select this pad when we copy, and then we paste. It's Ctrl C and Ctrl V, and we click in another direct position. But in this case, with the lower left X, we can assign the value in the datasheet, which is 1.3 millimeters. Lower left X, 1.3 millimeters. Okay, the next step is we are creating the third pad. So again, we copy and paste into another location. And also with this pad, we are creating the lower left Y is to -2. Also, when you are doing the copy and paste, you might notice that the grid of your layout is maybe too large. So we can also change that grid, which is I think is right click on an empty space of a layout, and you can change the grid spacing. I think right now we can change to 0.5 millimeters. And now we have like a finer grid. So the final step is we're creating the fourth pad. So we copy one pad and then we place another pad. Also, we need to change the width. So the fourth pad, the width is 0.9 millimeter. And you can see from the datasheet that this pad, it has some kind of alignment. I think for the last pad, you can try using alignment instead of like assigning the locations. Yeah. So let me if you click these two and in the edit align, you can align right, and then selecting the bottom two and also do the alignment at the bottom, and then you can get the location of the last pad. So it's basically 1 minus 2 of the last pad. Width 0.9, height 1 millimeters. Yeah. Once we have these 4 pads, now we are creating the ports for it. We see that the amplifier has 4 ports, but in the layout we need to assign 8 ports actually. So we have 4 ports to connect the amplifier, and another 4 ports at the edges of the pad so that we can connect the microstrip lines. Okay, so the way we're doing this is by so also in the layout we should also note that there is some requirement of the orientation. So you see in this kind of transistor, the left bottom pin is the first pin. So I can add some text here. So this pin is the first pin, and this is the second, this is the third, and this is fourth. So this orientation, it matches this kind of orientation. It matches the port we assign in the simulation model. So in order to assign the ports on to this layout, we just need to click this button. You can see there is like insert pin. So once we insert pin, we insert the first pin somewhere in the center. Right now we are having a very large grid, so we also need to change the grid spacing a little bit, even smaller, maybe to 0.1. So we insert the first pin to the center of this pad, and the second pin to also the location of the pad, and then third pin on the top right, fourth pin on the top left. So with these 4 pins, we can connect the with these 4 pins, we can connect the transistor model into the layout. And then with the 4 ports created, then we need to create another 4 ports at the edges of the path so that it can connect to the microstrip lines or transmission lines. So at the 5th port, we can collect to the bottom center of the first pad, and it will automatically align. Yeah, this is the 5th port, and also the 6th port, 7th port, and 8th port. And then we can press escape, and now we have 8 ports. And in this case, by opening the port editor, you can have a view of your 8 ports. You can also have some inspection. You can inspect the port in the port editor button and say there should be 8 ports, and okay, now we have the layout of this transistor. And the next step is we also need to create a layout for the resistor and inductor. But one good news is that they are sharing the same kind of packaging, which is the 0603. So I have previously searched on the pad specs of this component, and I can directly copy this. So we just need to close this layout. And also in the layout file, we also don't need we just need to delete the schematic because it's just a layout. So we only need one layout and one symbol file for the component packaging. And then what we do next is we can create another layout. And here we can type maybe 0603/RLC. This is like a packaging, and we create this layout. It will automatically have like a new cell with this layout. Yeah. Okay. So next we are creating the layout for the 0603 packaging. Also, we first select the conductor layer and then create a rectangle. Also two rectangles. So we create one rectangle and we assign the width and length. So if you look at the specs, so the width is actually 0.05 millimeters. And the height, which is the D in this figure, is 1 millimeter. And you also assign this location to the origin, which is 0, 0 in the left X and Y. And if you want to find your packaging, you can click this button. You can click this View All button, and it will automatically scale. Also, yeah, this is the first pad with the D is 1 millimeter and the width 0.95. The next step is we Control+C, copy the cell, copy this pad, and then we paste it to another location, and we can assign the spacing. So the spacing of this one, which is C1 plus C2, which is 1.6 millimeters. So on the right copper, we can assign this lower left X is 1.6 millimeters. and now we are having the RLC layout. So the next step is we create pins. Also, it's 2-part, but we need to assign 4 pins. 2 pins for the RLC simulation and another 2 pins for the microstrip line connection. So, following the same step, we assign the first 2 pins in the center of the path. The first pin, second pin, and another 2 pins at the edges of the path. Sometimes if you can't find it, you cannot snap, you can change the options on the snap mode. Here we can toggle the midpoint snap mode, so it will automatically find the center, the middle point of the shapes. So the 3rd point on the left and the 4th point on the right. And once you create these 4 pins, you can close it and also you can open the part editor and inspect each pins, see whether it's at the correct location. So the next step is we are creating the symbols for this for this footprint, so that we can arrange these components in our final layout. So let's open this layout, and then let's open the symbol of the transistor layout cell. Once you open this, you can see this is like the older symbol we're having. But I think there is a quick way of doing this. We can first delete this symbol, delete these 4 symbols, because we are assigning new pins, and we can here insert generate symbol. Generate symbol in the first tab there is auto generate, and we can select the source to layout and make them look alike. Maybe 3.3, and this one it looks better. And we repeat the same process for another layout. So we close this symbol.
Do you have to save it?
Yeah, you also, of course, you need to save it. Yeah, you need to save this. And then in this, yeah, I think if you select the 0603 RLC, right click, you can just add a new symbol and just create a symbol for this one as well. And also source view lookalike from the layout with the scaling of 0.3. You do this again, you can generate this view. Okay, so right now we have the package we want for the transistor as well as for the RLC. So what we are going to do next is we open the schematic we want to do the layout. So in my case, it's Sim4 layout. In your case, I think it should be the last schematic you have saved, except the SP cell. So when you open this layout, I think the first thing is we are just creating a layout, so we just need to disable. So we are just creating a layout, so it means that we will not run circuit simulations with this file. So we can select every components except the microstrip lines. We select all, and we press Shift, and we click the microstrip lines, and we disable them because we are just creating the layout. So we only we are only leaving out the components having the packaging or the layouts. So the next step is, once we disable everything except the transmission lines. We can also enable the substrate just in case the layout knows the substrate information. Then we click the library, and in the workspace libraries, you can see the components we have created. So we have 0603 ILC, and also we have the transistor layout. So first, let me just insert the ILC layout. And also we can insert the transistor layout. So what we can do next is we replace those RLCs with the layout instead of the components. I think you can, if you want to replace some component, you can just delete this. Component library. And you just need to replace those, the components with the layout we have.
Do we need to delete him, or?
Yeah, we can delete this because we were not simulating with this file. This schematic is only used to create the topology of the layout.
Did you save it?
Because when I have to find save schematic because I want to save it.
This is a copy of original.
I think it's the original.
You need to make a copy, yeah, because we are not doing the simulation with this file.
Close it and make a copy. Even there maybe C5.
Yeah.
Create a new one and copy and copy the schematic. Only yes, RLC, double click, and put nearby all the RLC components. Like with the inductor, capacitor, resistor. Nothing else. Save as. The new name, as backup, or yes.
I know, but I think it's this one and another. The other one we did. Right? There were two.
Another component?
Yeah.
Send
Oh, and the libraries. Yes, that's the one. I'll just
It should be your workspace. You could press on yes. So IRC, yes, double push for all IRC. Later you do a set for this one. Only one.
So we have the next all of the inductors.
The thing with that, then on the scene,
I think yeah. So basically, this is what we can get.
你为什么把它给放的重叠？你是把那个都
哪里
删了吗？
都删掉了。Because we are just generating a layout, so if you see there are some disabled components, you can just delete it.
Yeah. You can do what Ian did. Once you place the layout nearby the component, you just delete that component.
Yeah.
And that will be replaced by your layout.
Yeah.
有连线吗？连一个，就每端连一个。
You need to do the electrical connection between the layouts, and so once we have the layout imported and connected, we can click layout and generate layout. Generate layout, and we follow the default settings. Sync the entire design, and we click OK. And now we are having the layout, but we also need to rearrange these components because right now there are a lot of parts overlapping. So let's start from the source side. So here we can see that we need to have like open stop TL2 connected to TL1 and then to X2. So we can first find, so TL1, this is like an open stop, but we need to rotate this. Also press Ctrl plus R to rotate this component. TL2 is here, and TL1 we also need to maybe we can make it TL2 and TL1 is the through. Yeah, here this is the through, and TL2 is the open stop, and we can make it upwards, and also with the pins aligned. So this is the TL1 and TL2 connection, and for the TL1, it's connecting to X2, which is the RLC component. So also in the layout, we need to find the RLC component here. Yeah. So now we can have like a open stop transmission line, and this is the capacitor, and the next is we're giving an inductor. So this one is the inductor, and we can overlap pin by pin. So this capacitor, inductor, and then we can connect it to the transistor. So maybe you can first do the layout on the input side. You have the open stop, you have the through, the capacitor, inductor, and the transistor.
This one, like the large one, large one should be the left one.你感觉后面少的东西会出问题吗？
谁知道呢？有可能。
不都连好了吗？看这边，至少摆出来了。这样把它给挪到这上面。因为这个线它不是这么细的，肯定是不对的。首先你要把它给滚上来没问题。OK， 把它挪过来。这是 stop， 竖过来。然后把它重叠到一起就行了。两个蓝色的点 ，OK， 好了。同样把 component 也是，这个对，重过来，它线不都给你画好了，直接要连谁？对。
那这个，
真少，删了吧，没事。这种线反正是一点都不一样，删了，直接删了。你也可以在这提前就把这个线给删了，比如这种，对，这种，我把它删了，它还是有个白线的，并不会损失什么。你还是知道它其实该连它的，跟别人不一样，本来就没问题。然后拖它就行，这是个 start， 都是直接用 start， 把它给导过来，再导。好，让这两个蓝色的是上，就相当于两条线就连上。
所以这些线都要删吗？
对，不要删，其实这些线都要删，早晚都得删。然后删了过后，还是会留一条白线给你，然后你就跟着那个白线走。下一个这个蓝色的点该连哪个 component， 这是排列，把它给拖过来，拖到那个蓝色的点上，要结合一起。哎，对，我觉得
这可以看吗？可以。
我觉得您的对您的 size， 您怎么会是0.3？
不是
0.3，
不是，0603是0.3 inch。你的 pad 的话就可以画一个1毫米乘1毫米，然后间距1.7毫米。
所以你得回去先改封装。对，这个 layout 你就可以先关了，然后先回去把0603的封装给改。
是不是因为那个 scale
不，那个只是在建那个 symbol 的时候有一个 scale factor， 但 layout 是实打实的事情。
Also, I think when you generate layout, you may find that if you, at some points, you have pin-to-pin connection, and also at another point there is an issue. You cannot align this like 4 pins. Then you can also manually adding some coppers or traces to connect these lines. Because when we are doing the post simulation later, then we can also simulate the effect of these additional lines on the biasing.
This is like about 1 million. This is less than 1 million. Everything red is a texture line, and this is unwanted texture. To start the layout, you have to think your schematic. Schematic, for example, this one. So the fourth, go to the start and the custom line. Yes. Start here. Bold. Start here. Yeah. So, we can actually delete these things. Even if you delete it, there's still an indicator. I see the indicator. So you can safely delete all of it. They are all to connect them one by one. That's right. Bring the zero start. Yeah. And we can, here is the transition line. We will take it. See, they are placed close, and once we are very close, they attach. I see. Great. This white trace will guide us which is our next component to be connected. This is
Okay, so I think we can do the next step. So once we have this layout, the following step have nothing to do with any of the schematics we have done before. So this is one point I want to mention. So the next step is we are assigning ports on this layout so that in the later simulation we can find reference to give the excitation. So where should we assign these ports? Actually, we need to assign every port where we want to have like a electrical connection, whatever is like a DC or RF. So here, port 1, of course, we are assigning to the input, and port 2 we can assign to the output. And then port 3 and 4, then we need to have like a closer look. So here we have like a component of capacitor, and we can assign port 3 and 4 in the center of the pads for the capacitor. So port 3 and port 4, and port 5, 6, we can assign here to the inductor, port 5 and port 6 to the inductor of the center pads, and port 7 then we can assign to the DC pad on top. Port 8 we can assign to the resistor, which is like we can assign it here. This is port 8, and port 9 we can assign to another pad of resistor, and then port 10 to the ground. And then it's like a port 11, we can go upwards to select the capacitor. Port 11 to two sides of the capacitor. And next is port 13. 13 we can assign it to the inductor. Port 13, 14 and 15 to the inductor. And then 16 we can assign to the 4 ports of the pad of the transistor. So it's 16, 17, 18, and 19, and 19. So now in total we are having 19 ports of this layout. So basically one port in this layout is just one point of connection for our EM-CoSimulation later.19个单口。后面做后仿的时候，连接 SPICE、连接 excitation 还有文器件的。
所以在每一个上面都要有。
对，每一个你后面后仿要连接的点都要连一个。
每一个器件的两端吗？
对。
那它放在哪里都行。
对，我们之前不是留了那几个 pin 的位置吗？你可以直接放到那个 pin， 对，放到 pin 的位置。
那边缘没有？
边上只放了2个 port 呀。
边上放
板子边上2个，中间器件每个器件放1个。
每个器件中间放
对，每个器件中间放2个。对，然后有的器件边上有连接再放。And I think I also missed the 2 parts, which is the ground connection of the transistor. So I will add another 2 parts also to the edges of the transistor. So now we're having 21 pins, I think. Yeah, 21 pins.
Yeah, it didn't do it.
这就可以拍下来。
这玩意儿不是能教的，
这不应该放在1天里。
对，你要是正式培训的话是2天的课。
对啊
，Schematic 1天，布仿的要1天，1节课上完那就是1个下午。
是，还是在假设他们都上过那个课的情况下才能搞出这个。
So whatever number of pins you have assigned, in my case it's 21 pins, you need to make sure every pin here, except the open circuit of the 2 transmission lines, are turned into like a it's like a light blue color instead of like a crayon color. So there is only 2 ports unconnected, 2 pins unconnected, right? Except that every other pins are either connected to a port or connected to other pins. And in this case, we are having 21 ports. I want to see if we can make the pins a little bit smaller. Make them look a little bit smaller. I don't know how to do this. Preference pin. 2 pins. Does it work?
这哪是2个 pixel 的
Size units. 2个 layout unit
是2个毫米，应该比现在小一点。
没变化。
改了吧，改。
没问题的。Component text.
You're gonna send the Zoom to this recording to this.
Yeah, we have the recording.
Thank you.
You're welcome.
真3D 仿造。之前是用 ADCD 那个传输线理论来算的，现在是要用真的线做物理的调整。你光规定你还要给，比如2个线。 边要放 S 乘 B，你如果把数学改进出来的话，就后聘人是感觉。
那我就多了。
每一个除了那种连接的是不用的，但是这种对这种不用，左边这个不用，右边这个。
那我
你多少个一个？它是一个能对比。
但是我就把每个
一边比如 pad 跟 transmission 在连接点的那个 pin 是不用连的。
对，不用连。
那它连完了才21。
对，连完了21个。
那为啥你把那个连就是左边第一个？
哪一个？
左边第一个就是
这个呀。
对。
这个不是这个我们没加 port 呀，这个是它是两个microstrip line 连到一起，它就
自己连到一起。
对，它自己连在一起。
就变蓝色了。
对。
对，那你也应该这样变蓝色，但是不应该首先加后的。已经找不到了。这条线的。回去看 video 不够。你发北京不可能的。
我给你发的就是两个切片机的。
pad 不是有的在 pad 中间嘛，有的在 pad 边上，中间的你要连到后边，因为我们待会儿比如要放 RLC 上去，但是 pad 边上的边上那个是金属 contact 跟其他走线啊什么的。
那这个
要放一个 pin 上去，这个就不放，这是对的。
然后这个
那 stop 下端永远不会。对，上面已经连上了，但是这儿要额外加个 port 的原因是，这是你的 port 2，是你的 port 1跟 2，是让你 simulation 的 port， 那很重要。这个不用连 port， 但是你已经连上了，你是 contact 上很好，没啥问题。
因为这个不用连。
不用连，不搞它了。要额外加手动 port 的是这
中间的
个
边缘。
中间都是比如这个，对，因为这个不用，因为你让他，但是要仿真，他知道你的东西已经让你做了。
那这里面是这不用连。
这是边上，有个边上的分管，但是这个这三个是加数字，那这两个要加一个加什么？这是要加什么？这是要加 S 2的，这个要有。
Here it is. I don't know if it works, but here it is.
I cannot define.
我觉得没有。
It's far away from that we can find errors.
It's past the point.
Let's later try to simulate it. If this works, very good. If not working, we have to start from the schematic, not from beginning, just from
Do you mean the circuit?
Yes.
So last doesn't work in this way.
Yeah. Yes.
Okay.
就后面他们说把你的这个正规的这个文件传给他们。
OK。
对，他们也怕自己可能照着做都不一定再做重复出来，那就开始下一个。
好用了吗？好用啊！听讲完了。
但是我真没有，我真的当时是好像有点这样的知识。
仿真的两后加，加上至少都是还是一个加。这是你的不，这是 stop，
这两个。
对，这是 不是我吧，我不想看。
Okay, so
下一步人好就
so
好
the next step, we are assigning the substrate to this layout. Once we click the substrate, we will OK, and we can create a new substrate. We can call it FR4 or substrate 1 or whatever. And in the template, we can select a 2-layer FR4. So right now it's FR4, 2-layer FR4, and then we can create a substrate. So you see now it's a 3-layer conductor. We just need to remove 1 layer. So we click the top dielectric and we right click it, and then we can delete with lower interface so that there is only 1 layer. And on the first conductor layer, we can assign this layer from PC3 to conduct. Maybe it is COND. Yeah, the layer should be conduct. And thickness, as according to our simulation, is 50 micron. So this is what we have in the first layer. Conductor layer, the name should be conduct 1. Or if there is any other chances of conduct. And then we collect the dielectric. It shows FR4, but we need to change its thickness to 2.5 millimeters. And also the material, once we click the 3 dots of the material, we change the permittivity from 4.6 to 4.0, I guess. Yeah, 4.0. And that's it. Also, on the bottom layer of the conductor, we select this and we assign a layer to conductor 2. And then we also need to change the layer thickness to 50 micron. And then we save this substrate. Once we save the substrate, we can close it. And then we click the EM simulation settings. We create a new EM setup view. So we create new EM setup view. So in the EM setup for this layout, we first create the setup type to EM-CoSimulation and the EM simulator using the momentum microwave. And by clicking the layout, we can check if you are using the layout, which is the layout we are using, and also partitioning, substrate, ports. We can go through this and see. We can also refresh the ports. And frequency plan, of course, we need to sweep from 1 gigahertz to 3 gigahertz with 21 number of points. Frequency plan, and then output plan. We don't need current plots, so we just leave it as is. So when we finish every setup, on the bottom right corner there is like generate views. So we first select generate views and we press go. Then it shows that the co-simulation layout is successfully created. To check the layout, we can click this button. It says 3D EM preview. We can click this EM preview. And later it will plot our 3D like a simulation model. But I think there is one step we are missing is we cannot see the ground plane, right? We didn't find a ground plane. So we close this 3D preview. We close this EM setup. Into our layout, we switch back to conductor 2 layer, and we are drawing a rectangle as the ground plane. So the ground plane it should be covering every circuit we are having. We can also make it a little bit larger. So I think the recommended minimum size should be larger than 3 times the width of the microstrip line we are using. Yeah. So after the resizing, now we have the design with the ground plane. And after we create the ground plane, we click back to the EM simulation setup settings. And again, generate at the bottom right, generate views, and we press go to update the view. So of course we need to continue and rewrite. And then let's look at the processed 3D view. So it looks like there is something missing. So we can see there is a ground plane and our substrate. Once we click the shade, we have the substrate and the ground plane, but we cannot we didn't see the ports. So it means that we also need to update some information of the ports so that the EM simulator can identify the ports. So we click the ports of the EM setup and we update. It looks like we didn't specify the ground layer. So we need to update this by clicking the open layout editor, open layout port editor. We need to assign the ground layer. So right now it's implicit, but we can select it to conductor 2 by typing C, and then you can go to conductor 2. So we need to repeat this process for every port. So it's 21 ports. Yeah. So Okay, once we updated these ports, we can first click the refresh the port and pin data, and then close the port editor and save the layout. Okay, after saving the layout, we go back to the EM setup. So we click OK to accept the changes, and in the ports, we refresh it again. We refresh the ports again and see. Now we can see the ground layer is already assigned, and we can generate the views again. So we override our existing views, and then here in the layout, we can see there is a button show 3D EM view. If we click this button, and later we'll have a pop-up window, and now you can see there are already ports highlighted here. So if you look at the ports, you see there are 21 ports assigned. 21 ports assigned from port 1 to port 21 in its corresponding locations. So you see there is in the center of the path, in later we'll connect the circuit model on this, and on the edge of the pad we'll connect either ground or like a DC excitation or the S parameter ports. Yeah. So right now it looks like we are in the correct configuration of the layout, and we can close this view. We close this 3D preview, and we save this setup. So on the bottom right, generate. This time we generated EM-CoSimulation input files, and we press go again. And then we do the overwriting. And next we are generating mesh. We click generate views and mesh and go. And we overwrite this again. So the simulator will pop up and do the meshing at 3 GHz. So when it says status done, you can close this and save the EM setup and close the EM setup. And in the layout, now we can see the generated mesh with the assigned port as well. Okay, so now right now we have a layout and we have the mesh and we have the ports. So next we're going to create a symbol. But as you can see, there is also another issue with this cell, is that we want to referring our layout to other simulations, but there is another schematic of this layout, which means that this will have conflict when we later on doing simulations. So therefore, we can open the schematic of this layout, and we can save it as in another cell, so that we can move this outside. So once we save this cell as a backup, we go back to our layout and we delete our schematics. So in this case, we don't need the schematic anymore. For the EM part of the co-simulation, we only need a layout and the simulation setup. So this is a very important step for this co-simulation. Make sure that it looks like in the ADS, whatever cell you are referring to, if you're using its layout, you should make sure there is no schematic inside. Otherwise, it will have a lot of conflicts when updating the layout. Okay, so right now what we have is we have the EM setup, simulation setup, and also the layout here. And once we open the layout with the mesh, and we open the EM simulation setup settings here, you can see there is a symbol here, open symbol editor. So now this time we'll click open symbol editor, and it will create a new symbol, and we can auto generate from our layout and look alike. And then in this case we can use like scaling factor. I think we can follow the same scaling factor, 0.3, and then we click OK. Now we can have our complete layout as a symbol. Yeah.
How do you determine the scaling factor?
Trials and error.
Just trial and error.
Yeah.
So we should use 0.3?
Yeah, you can use 0.3 for this unit. Yeah. You can start from 1 and see if it's too large, and then we can make it smaller and smaller.
Yeah.
Okay, so we are now going to do the last about 2 steps. So we'll create a new schematic, but with the importing this layout as a complete component. So what we do next is let me just close every open file first, and then we can create a new schematic, and we can change its name. Same file, in this case is EM, and in this new open the schematics, we can open the library browser. In the workspace libraries, we will find our Sim4 layout. We double click this, and now we are importing our layout as a component. So what we will do next is we can just open our previous simulation schematics. In this case, here we can open this SPNF this file, and we can directly copy our models and also with ILC components into our layout. It looks like our layout is a little bit smaller, so maybe I'll update the scaling a little bit as well. Here maybe 0.5 or 0.6 to make it larger. And we insert the layout again.
Then you think he's included consistent.
Yep, the same. This is schematic, so you have
Okay,
to
so-
put your everything. For example, this is one from this one.
And once we put
There's a mismatch.
our transistor, we connect it to the pads,
And RLC, everything, and port 1, port 2, ECs.
and we can connect the ground plane to other pads.
And this, if it's not matched, right? But the wire this time is coming in the wire.
Okay, so that's
Just like this.
Assigning the ports to the end.
wire.
hook like this is not working. You still need to use wire. But you have to remember what is the order.
Yes, because mine was like flipped.
Capacitors,
We are
inductors,
at the same direction as you.
resistors, and the DC source.
GDSS to the ports. Remember, I think it's this. Yes. So, however, you have to use wire. Yes, you use wire. So the criteria is still there.刚才不是给你 generate symbol 了吗？删掉了。再 generate 一次。你自己的名字记得吗？你刚才给的那个 layout create 有一个 symbol 出来，所以它就叫 Sim4 layout。所以然后在 library 在你 library 对 Sim4 layout 对就上双击放大这么大的 symbol。有点挨着一点，第二个这个好一点。然后到下一个 mesh， 还在跑。没事 ，skill 选选没那么重要，说小也没那么重要，反正看，比如再把这个调进来，哎，对，他说这一句。肯定是有这种会差。你是把它覆盖列的也好，上面不用看，旁边是。
So we are basically repeating our previous schematic layout, except that we changed the connection, changed the paths, and changed the microstrip line with our layout component, and we're reconnecting every component to the layout using the ports we're giving. I think you can keep the scale factor to 1 if you want.
How can I change that?
You open the symbol and delete everything, and you run the import wizard again.
你真的没有那个 symbol 你改了一个，你把 symbol generate 5 hours in small hours 5 hours the result. That's just